zero to millions of users. Designing a system that supports millions of users is challenging, and it is a journey that requires continuous refinement and endless improvements. In this chapter, we will build a system that supports a single user and gradually scale it up to serve millions of users. After reading this chapter, you will master a handful of techniques that will help you crack the system design interview questions. Single server setup. A journey of 1,000 miles begins with a single step, and building a complex system is no different. To start with something simple, everything is running on a single server. Figure shows the illustration of a single server setup where everything is running on one server: web app, database, cache, etc. So here, user user is using web browser or mobile app, and it is making a call to api.mysite.com to DNS, and in turn DNS is returning its IP address, and then it is making a call to our server using our URL. There can be multiple URL mapped to basically this same endpoint. To understand this setup, it is helpful to investigate the request flow and traffic source. Let us first look at the request flow. This is a user uh, just numbered the request or how it will go and come. The users access websites through domain names such as api.mysite.com, usually the domain name system. DNS is a paid service provided by third parties and not hosted by our server. Internet protocol IP address is returned to browser or mobile app. In this example, IP address is 15.125.23.214 is returned. Once the IP address is obtained, Hypertext Transfer Protocol (HTTP) requests are sent directly to your web server. The web server returns HTML pages or JSON response for rendering. Next, let us example the traffic source. The traffic to your web server comes from two sources: the web application and mobile application. Web application, it uses a combination of server-side languages, Java, Python, etc., to handle business logic, storage, etc., and client-side language, HTML and JavaScript, for presentation. Mobile application HTTP protocol is the communication protocol between the mobile app and web server. JavaScript object notation JSON is commonly used API response format to transfer data due to its simplicity. An example of the API response is JSON format is shown below. This is the endpoint get for users 12, retrieve a user object for id is equal to 12, and we got one JSON. Database. With the growth of the user base, one server is not enough. We need multiple servers, one for web mobile traffic, the other for database. Separating web mobile traffic, web tier, and database, data tier, server allows them to be scaled independently. Which database to use? You can choose between traditional relational database and non-relational database. Let us examine their differences. Relational databases are also called a relational database management system, RDBMS, or SQL databases. The most popular ones are MySQL, uh, Oracle database, and Postgres SQL database, etc. Relational databases represent and store data in tables and rows. You can perform join operations using SQL across different database tables. Non-relational databases are called NoSQL databases. Popular ones are CouchDB, Neo4j, Cassandra, HBase, Amazon DynamoDB, etc. These databases are grouped into four categories: key value stores, graph stores, column stores, and document stores. Join operations are generally not supported in non relational databases. For most developers, relational database are best option because they have been around for 40 years and historically they have worked well. However, if relational databases are not suitable for a specific use case, it is critical to explore beyond relational database. Non-relational database might be the right choice if your application requires super low latency, your data are unstructured, or you do not have any relational data. You need to serialize and deserialize data, JSON, XML, YML, etc. You only need to serialize and deserialize data. You need to store a massive amount of data. Vertical scaling versus horizontal scaling. Vertical scaling, referred to as scale up, means the process of adding more power, CPU, RAM, etc. to your servers. Horizontal scaling, referred to as scale out, allows you to scale by adding more servers into your pool of resources. When traffic is low, vertical scaling is a great option, and the simplicity of vertical scaling is its main advantage. Unfortunately, it comes with serious limitations. Vertical scaling has a hard limit. It is impossible to add unlimited CPU and memory to a single server. Vertical scaling does not have failover and redundancy. If one server goes down, the website app goes down with it completely. Horizontal scaling is more desirable for large scale applications due to the limitations of vertical scaling. In the previous design, users are connected to the web server directly. Users will unable to access the website if the web server is offline. In other scenario, if many users access the web server simultaneously and it reaches the web server's load limit, users generally experience slower response or fail to connect to the server. A load balancer is the best technique to address these problems. Load balancer. A load balancer evenly distributes incoming traffic among the web servers that are defined in a load balance set. Shows how a load balancer works. Domain, this is the domain and IP. All the setup are almost same. This is our user and it is making a call to a public IP. And now here, instead of calling directly to the server, we have added a load balancer, and now it is based on my IP address. It will distribute it will give my call to a particular server. As shown in figure 1.4, users connect to the public IP of the load balancer directly. With this setup, web servers are unreachable directly by the clients anymore. For better security, private IPs are used for communication between servers. A private IP is an IP address reachable only between servers in the same network. However, it is unreachable over the internet. The load balancer communicates with the web servers through private IPs. In figure 1.4, after a load balancer and a second web server are added, we successfully solved no failover issue and improved the availability of the web tier. Details are explained below. If server 1 goes offline, all this traffic will be routed to server 2. This prevents the website from going offline. We will also add a new healthy web server to the server pool uh, to balance the load. If website traffic goes rapidly and two servers are not enough to handle the traffic, the load balancer can handle this problem gracefully. You only need to add more servers to the web server pool, and the load balancer automatically it starts to send requests to them. Now the web tier looks good. And what about the web data tier? The current design has one database, so it does not support failover and redundancy. A database replication is a common technique to address those problems. Let us take a look. Database replication, quoted from Wikipedia. Database replication can be used in many database management systems, usually with a master slave relationship between the original master and the copies slaves. A master database generally only supports write operations. A slave database gets copies of the data from the master database and only supports read operations. All the data modifying commands like insert, delete, or update must be sent to the master database. Most application requires a much higher ratio of reads to writes. Thus, the number of slave databases in a system is usually larger than the number of master databases. Figure 1.4 shows a master database with multiple slave databases. This writes to master DB, and whenever web servers request a read call, it goes to the slave databases. And at the same time, data replication keeps happening from master database to slave database. Advantages of database replication: better performance. In the master slave model, all writes and updates happen in master nodes, whereas read operations are distributed across slave nodes. This model improves performance because it allows more queries to be processed in parallel. Reliability. If one of your database servers is destroyed by natural disaster such as typhoon or an earthquake, data is still preserved. You do not need to worry about data loss because data is replicated across multiple locations. High availability. By replicating data across different locations, your database remains in operation even if database is offline, as you can access data stored in another database server. In the previous section, we discussed how a load balancer helped to improve system availability. We asked the question here: what if one of the database goes offline? The architectural design discussed in figure 1.5 can handle this case. If one slave database is off available and it goes offline, read operations will be directed to the if only one slave database is available and it goes offline, read operations will be directed to the master's database temporarily. As soon as this issue is found, a new slave database will replace the old one. And in case multiple slave databases are available, read operations are redirected to other slave databases. A new database server will replace the old one. If the master database goes offline, a slave database will be promoted to a new master. All the database operations will be temporarily executed on the new master database. A new slave database will replace the old one from data replication immediately. In production systems, promoting a new master is more complicated as this data in a slave database might not be up to date. The missing data needs to be updated by running recovery scripts. Although some other replication methods like multi-masters and circular replications could help, those setup are more complicated and their discussions are beyond the scope of this book. Interested readers could refer to the listed reference materials. 4.5. Figure 1.6 shows that system design after adding the load balancer and data replication. Again, these are the user, this is the DNS server, and I asked the my site what is the IP address of this mysite.com. It gave me an DNS provided me the IP address, and then I made the call. All the call went to load balancer, and then load balancer calls the private IP addresses of the servers. This is the web tier, and then all a server will if there is a write call, it will write to the master DB, and it will at the same time got replicated to the slave database. And if they and whenever the read calls will come, slave databases will handle it. This is our data tier. Now, let us take a look at the design. A user gets the IP address of the load balancer from DNS. A user connects to load balancer with this IP address. The HTTP request is routed to either server 1 or server 2. A web server reads user data from a slave database. A web server routes any data modifying operations to the master database. This includes write, update, and delete operations. Now you have a solid understanding of the web and data tiers. It is time to improve the load response time. This can be done by adding a cache layer and shifting static uh, content, JavaScript, CSS, image, video files to the content delivery network, CDN. Cache. A cache is temporary storage area that stores the result of expensive responses or frequently accessed data in memory so that the subsequent requests are served more quickly. As illustrated in figure 1.6, every time a new web page loads, one or more database calls are executed to fetch data. The application performance is greatly affected by calling the database repeatedly. The cache can mitigate this problem. Cache tier. The cache tier is temporary data store layer, much faster than the database. The benefits of having a separate cache tier includes better system performance, ability to reduce database workloads, and the ability to scale and cache tier independently. Figure 1.7 shows a possible setup of a cache server. If data exists in cache, read data from cache. Um, Return data to the web server. If data does not exist in cache, save data to cache. So basically what is happening, if the first call is, if the web server will hit the cache, and if data exists in cache, some data will be returned back to the web server. If but if if data is not present in the cache, it will again the call will go to the database, and then it will come back, and its way back it will also update the cache with the new data, and the response will return to the web server. After receiving a request, a web server first checks if the cache has the available response. If it has, it sends back to the client. It sends data back to the client. If not, it queries the database, stores the response in the cache, and sends it back to the client. This caching strategy is called a read through cache. Other caching strategies are available depending on the data size, data type, size, and access pattern. A previous study explains how different caching strategies work. Interacting with cache servers is simple because most cache servers provide APIs for common programming languages. The following code snippets shows typical memcached APIs. Seconds is equal to 1, cache.set, my key, hi there, and 3600 into seconds. Cache.get, my key. So this is just setting the key. The key here is my key, and the value is high there, and for how long it will stay in the cache. That is 3600 into 1. So this many seconds it will store into the cache, and then when how will you fetch the data from the cache? By just simply saying cache.get and giving the key. Consideration for using cache. Here, few consideration for using a cache system. Decide when to use cache. Consider using cache when data is read frequently but modified infrequently. Since cache data is stored in volatile memory, a cache server is not ideal for processing data. For instance, if a cache server restarts, all the data in memory is lost. Thus, important data should be saved in persistent data stores. Expiration policy. It is a good practice to implement an expiration policy. Once cache data is expired, it is removed from the cache. When there is no expiration policy, cache data will be stored in the memory permanently. It is advisable not to make the expiration data too short, as this will cause the system to reload data from database too frequently. Meanwhile, it is advisable not to make the expiration date too long, as the data can become stale. Consistency. This involves keeping the data store and the cache in sync. Inconsistency can happen because data modifying operations on the data store and cache are not in single transaction. When scaling across multiple regions, maintaining consistency between the data store and cache is challenging. For further details, refer to the paper titled Scaling Memcached at Facebook, published by Facebook. Mitigation failures. A single cache server represents a potential single point of failure, SPOF, defined in Wikipedia as follows. A single point of failure, SPOF, is a part of the system that, if it fails, will stop the entire system from working. As a result, multiple cache servers across different data centers are recommended to avoid SPOF. Another recommended approach is to over provision the required memory by certain percentages. This provides a buffer as the memory uses increases. Um, so web server, this is the router. If and then router is making call to different machines, and if this router fails, this is our single point of failure because it will take down entire communication. Eviction policy. Once the cache is full, any request to add items to the cache might cause existing items to be removed. This is called cache eviction. Last recently used, LRU is the most popular cache eviction policy. Other eviction policies such as read frequently used or first in first out can be adopted to satisfy different use cases. Content Delivery Network (CDN). A CDN is a network of geographically dispersed servers used to deliver static content. CDN servers cache static content like images, videos, CSS, JavaScript files, etc. Dynamic content caching is a relatively new concept and beyond the scope of this book. It enables the caching of HTML pages that are based on a request path, query strings, cookies, and request headers. Refer to the article mentioned in reference material for more about this. This book focuses on how to use CDN to cache static content. Here is how CDN works at high level. When a user visits a website, a CDN server closest to the user will deliver static content. Intuitively, the intuitively, the further users are from CDN servers. The slower the website loads, for example, if CDN servers are in San Francisco, users in Los Angeles will get content faster than users in Europe. Figure 19 is a great example that shows how CDN improves load time. This is this is client. The client has to make call to the origin, which was taking 120 milliseconds, but if the client make calls to the CDN, it only takes 40 milliseconds. Now figure 110 demonstrates the CDN workflow. Suppose user 1 wants to get an image. He calls the CDN. If CDN if not in CDN, get the image from the server, then store then on the way back store the image in the CDN and then return the image back to the user. And again the same thing happens. User B asks for the same image, but now we just updated our CDN, so we know so obviously the image is already present, so we don't have to make a call back to the server. So the stored image in the CDN will be returned to the user B. Now what is happening is explained. User A tries to get image point png from using an image URL. The URL's domain is provided by the CDN provider. The following two images URLs are samples to use to demonstrate what the image URL look like on Amazon and Akamai CDNs. HTTPS mysite.cloudfront.net logo.jpg and one more endpoint. If the CDN server does not have image.png in the cache, the CDN server requests the file from the origin, which can be a web server or online storage like Amazon S3. The origin returns image.png to the CDN server, which includes optional HTTP header time to live, which describes how long the image is cached. The CDN caches the image and returns it to the user A. The image remains cached in the CDN until the TTL expires. User B sends a request to get the image. The image is returned from the cache as long as the TTL has not expired. Considerations of using a CDN. Cost. CDNs are run by third party providers and you're charged for data transfers in and out of the CDN. Caching infrequently used assets provides no significant benefit, so you should consider moving them out of the CDN. Setting an appropriate cache expiry for time sensitive content, setting a cache expiry time is important. The cache expiry time should neither be too long or too short. If it is too long, the content might no longer be fresh. If it is too short, it can cause repeat loading of content from origin servers to the CDN. CDN fallback. You should consider how your web application copes with CDN failures. If there is temporary CDN outage, clients should be able to detect the problem and request resources from the origin. Invalidating files. You can remove a file from the CDN before it expires by performing one of the following operations. Invalidate the cache object using APIs provided by CDN vendors. Use object versioning to serve a different version of the object. To version an object, you can add a parameter to the URL such as version number. For example, version number 2 is added to the query string image.png and version is equal to 2. Shows the design after CDN and cache are added. Users, DNS, and then CDN. So it first make call to the CDN, and if call fails, then the load balancer servers and databases gets the call. Static assets, JS, CSS, images, etc., are no longer served by web servers. They are fetched from CDN for better performance. The database load is lightened by caching data. Stateless web tier, that will we will read later on.